Yes. Great. I propose we start in about a minute, 2 or 3 minutes, just to let the participants join as well.
Andre, do you think now is a good time to get started?
1 minute more and then okay. We go. Clément, maybe if you just unshare the screen, just for the start.
Yeah.
Great. Then we go on. Great. Hello to everybody. This is the 8th One World YoungStatS webinar in our webinar series. YoungStatS project is a project taking place in the framework of Young Statisticians Europe initiative of the YoungStatS Association and supported by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics, IMS. Today's topic is advances in differences in econometrics. We have, I will say, leading scholars with us, for leading speakers and great discussant, Pedro Sant'Anna with us. I will shortly present them. We have Clément de Chaisemartin of Sciences Po in Paris, Jonathan Roth of Brown University of USA, Brantly Callaway, University of Georgia, USA, and Li Hualei, currently at Stanford University, USA. And our discussant, as I mentioned, is Dr. Pedro Sant'Anna of Microsoft and Vanderbilt University. USA. So we will start with Clément de Chaisemartin, and I assume many of the features of difference in difference approaches, at least those who are from econometrics, surely know many things about this, so we will not introduce them. Especially, they are one of the predominant approaches to address causal inference today in social sciences, econometrics, all around. So I give the floor to Clément for the first presentation.
Andre, can you just make me the host? Thank you.
Immediately. Yes.
Yep. Perfect. Thank you. Okay, thank you very much to everyone for coming, and to Pedro and Andre for organizing. So I'm going to present a survey about the recent literature on two-way fixed effects and diffs in diffs with heterogeneous effects. And my name is Clément de Chaisemartin, and I'm at Sciences Po. Okay, so to estimate the effect of a treatment or a policy on an outcome, researchers often run two-way fixed effects regressions. So for instance, if you're trying to estimate the effect of the minimum wage on employment, you would regress the employment in county G and year T on county fixed effects, year fixed effects, and the minimum wage in county G and year T. Such regressions are extremely pervasive in economics. 26 of the 100 most cited papers published by the American Economic Review from 2015 to 2019 estimate two-way fixed effect regressions. And those regressions have also commonly been used in political science, sociology, environmental sciences. Researchers have long thought that two-way fixed effect estimators are equivalent to diff in diff estimators, DID. A DID estimator compares the outcome evolution from a period T1 to T2 between two groups, a treatment group S that switches from untreated to treated, and a control group N that's untreated at both dates. And this DID estimator here relies on a parallel trend assumption that says that without treatment, both groups would have experienced the same outcome evolution. The evolution of their untreated potential outcome from T1 to T2 would have been the same in group S and in group N, the never treated group. Under this parallel trend assumption, it's possible to show that the DID estimator here is unbiased for the average treatment effect in group S at T2. And the proof of that just relies on the realization that of those four outcomes here, only the outcome of group S at time T2 is a treated potential outcome, while the remaining three are untreated potential outcomes. And then we just add and subtract the untreated potential outcome of group S at time T2, like I'm doing here. And finally, that term here cancels out owing to the parallel trends assumption. The parallel trends assumption is partly testable by comparing the trends of the two groups before group S got treated. So recent research has shown that unlike diffs in diffs, two-way fixed effect estimators are unbiased for some average treatment effect if parallel trends holds, but also if the treatment effect is constant between groups and over time. And this is often an implausible assumption. In the minimum wage example, you would expect that the effect of the minimum wage on employment is going to be different in US counties with highly educated workers and in counties with less educated workers. And so the realization that the most commonly used method in quantitative social sciences relies on an implausible assumption has spurred very many papers diagnosing the seriousness of this issue and proposing alternative estimators. And this survey is going to provide an overview of this recent literature. So we're going to start by papers that have shown that two-way fixed effect estimators are not robust to heterogeneous effects. So in a paper with Xavier, we've shown that under the parallel trends assumption, the expectation of the two-way fixed effect estimator is equal to the expectation of a weighted sum of the treatment effect in group G at time t across all the GT cells that are not untreated, and the WGT are weights summing to 1. The WGT weights are not proportional to the population of cell GT, and accordingly, beta at FE may be biased for the average treatment effect across all the treated GT cells. But perhaps more worryingly, some of those weights may be negative, and in that case, the two-way fixed effect estimator does not satisfy what is called the no-sign reversal property. Its expectation could, for instance, be strictly negative, even if the treatment effect is strictly positive for every group and time period. The two-way FE weights stay down R commands compute the weights WGT attached to any two-way fixed effects regression, and thus allow researchers to assess if or not their two-way fixed effect estimator estimates a convex combination of effects. Now let's try to understand the origins of this problem. First, when the treatment is binary and staggered, meaning that you can switch into the treatment, but once you're treated, you cannot switch out of the treatment, Goodman-Bacon shows that the two-way fixed effect estimator is a weighted average of two types of diffs in diffs. The first type are diffs in diffs comparing a group S switching from untreated to treated to a group N that's untreated at both dates. And this diff in diff is exactly similar to the one we saw earlier. And so it's going to identify a treatment effect only under a parallel trend assumption. But then we have the red diffs in diffs, the bad ones, that compare a switching group S to an always treated group A. And the negative weights in our decomposition of the two-way fixed effect estimator come from that second type of diffs in diffs. Now let's try to understand why. At both time periods, the always treated group is treated, and accordingly, its outcome is its treated potential outcome, which you can write as the sum of the untreated outcome plus the treatment effect. Accordingly, the outcome evolution from T1 to T2 in that always treated group is equal to the evolution of the untreated potential outcome plus the evolution of the treatment effect. On the other end, the switching group is only treated at T2, and accordingly, its outcome evolution from T1 to T2 is equal to the evolution of its untreated outcome plus its treatment effect at time T2. Then, when we combine those two equalities and take expectations, we get that the second type of diffs in diffs identify a weighted sum of three treatment effects, the effect in group S at T2, in group A at T2, in group A at T1, where one of the effects is going to enter with a negative weight, and that's the effect in group A at time T2. Okay, and the Y0 terms, when I'm taking expectation, cancel out under the parallel trend assumption. And so you see that this effect enters with a negative sign here, and that's why it may then enter in with a negative sign as well in our decomposition. And so the Bacon decomp state on R packages compute all the diffs in diffs that enter in the two-way fixed effect estimator. When the treatment is not binary or the design is not staggered, beta at FE may also leverage another type of quote-unquote bad diffs in diffs. And those are diffs in diffs comparing a group M whose treatment increases more to a group L whose treatment increases less. And in a previous paper about fuzzy diffs in diffs, we had shown that such diffs in diffs are also not robust to heterogeneous effects. And we can see that in a very simple example where we have a group M going from 0 to 2 units of treatment, while L goes from 0 to 1 unit. And we assume that potential outcomes are linear in the number of treatment units with slopes that represent the treatment effect that are different in the two groups. The two groups have strictly positive slopes, but the slope is 3 times larger in the group whose treatment increases less. Then, under the parallel trend assumption, we have that this diff in diff comparing group L and M is going to have an expectation that's going to be strictly negative despite the fact that both groups actually have a strictly positive treatment effect. So that diff in diff may again be a very misleading measure of the treatment effect. And intuitively, the reason is that the treatment increases twice as much for group M than for group L, but the treatment effect is 3 times larger for group L, and accordingly, the outcome of group L ends up increasing more than that of group M. Okay, and now the last thing I want to say is that dynamic two-way fixed effects regression also are not robust to heterogeneous effects. So with a binary and staggered treatment, researchers have often estimated dynamic two-way fixed effects regression, where YGT is regressed on group and time fixed effects, and on those relative time indicators that are equal to 1. For instance, that one here would be equal to 1 if group G started receiving the treatment L+1 periods ago. The idea is that for L greater than 0, this beta at L coefficient is supposed to estimate the cumulative effect of having been treated for L+1 periods. And for values of L lower than 0, those coefficients are supposed to be placebos comparing the outcome trends of groups that will later get treated and groups that will not get treated later. Actually, Sun and Abraham showed that under parallel trends, the expectation of beta at L as this expression here, where TEGL is the effect of L+1 treatment periods in group G. The first summation is a weighted sum across groups of the effect of L+1 treatment periods with weights that may be strictly negative. And so that shows that this coefficient is not robust to heterogeneous effects, because if the effect of L+1 treatment periods varies across groups, you could have that this summation here is strictly positive, even if, for instance, all of those treatment effects are strictly negative. And this term here, this first summation here, is pretty similar to the one we had in our earlier decomposition, in the one we saw 2 slides ago. Now we also have the second summation here, which is a weighted sum across L prime, values of L prime different from L, of the effects of L prime plus 1 treatment periods. And that shows that beta L, that's supposed to estimate the effect of having been treated for L+1 periods, is actually contaminated by the effects of having been treated for L prime plus 1 periods. And so the even study weights data package computes the weights attached to this decomposition here. Okay, so now let's discuss some of the heterogeneity robust diff in diff estimators that have been recently proposed. So first, in the paper I mentioned earlier, we assume the weight dynamic effects, meaning that we assume that the current outcome only depends on the current treatment, not on past values of the treatment. Then, with a binary treatment, we proposed to use the DIDM estimator, which is a weighted average across time periods of 2 types of diffs in diffs. The first diffs in diffs compares the T-1 to T outcome evolution of groups that go from untreated to treated and of groups that are untreated at both dates, while the second diffs in diffs compares the T-1 to T outcome evolution of groups treated at both dates and of the switchers out that go from treated to untreated. This first diff in diff is going to rely on a parallel trend assumption on the untreated outcome. The second one will rely on a parallel trend assumption on the treated potential outcome. And we propose placebo estimator to test those 2 assumptions. This estimator can be extended to discrete treatments, and it's computed by the DID multiple GT state on our comments. Now we're going to review some estimators that allow for dynamic effects with a binary and staggered treatment. With dynamic effects, the outcome of group G at time t is allowed to depend not only on our current treatment, but also on past treatments. And then Callaway and Sant'Anna and Sun and Abraham have proposed to replace the parallel trend assumption on the potential outcome without treatment by a parallel trends assumption on the outcome without having ever been treated YGT of ball 0t, where ball 0t is a 1 times t vector of zeros. So all the assumptions we're going to review now rely in one way or another on that type of assumption. So first, I would like to review the estimators proposed by Callaway and Sant'Anna, keeping in mind that even though I'm not reviewing them today in the interest of time, Sun and Abraham have also proposed estimators that are in some ways related. So the starting point of the paper by Callaway and Sant'Anna is that with a binary and staggered treatment, groups can be aggregated into cohorts that start receiving the treatment at the same period. So then Callaway and Sant'Anna define their parameters of interest as the average treatment effect at period C plus L of the cohort that started receiving the treatment at period C. And to estimate this type of parameters, they propose a diff in diff that compares the C-1 to C plus L outcome evolution in cohort C and in never treated groups. Then they also propose estimators of more aggregated effects. For instance, the average effect of having been treated for L+1 periods across all the groups that reach that treatment horizon over the duration of the panel. They also propose estimators using the not yet treated as controls rather than the never treated, because you may not have never treated actually. And they also propose estimators relying on a conditional parallel trends assumption rather than unconditional parallel trends. And their estimators are computed by the CS-DID and DID state arm or commands. Then Borusiak, Jaravel, and Spies have proposed alternative estimators. They're obtained from a two-way fixed effects regression of the outcome on group and time fixed effects, as usual, but also fixed effects for every treated GT cell. And their estimator of the treatment effect in treated cell GT is just going to be the coefficient on that cell's fixed effect. Under parallel trends and the assumptions of the Gauss-Markov theorem, this estimator is actually the linear unbiased estimator of the treatment effect in cell GT with the lowest variance, and then it's more efficient than the estimators in Callaway and Sant'Anna. And those estimators are computed by the DID imputation data package. So now let's try to understand the difference between, henceforth I'm going to say CS and BJS's estimators. Let's try to understand the difference between those estimators in a very simple example, where we have one treated group S that starts to receive the treatment at period TS, and all the other groups are control group. In that case, CS's estimator of that group's effect at period TS plus L periods after it started receiving the treatment, is equal to the difference between that group's outcome at TS plus L and that group outcome at the last period before it got treated, TS minus 1, minus the same difference, but taken on average across all the control groups. On the other hand, BJS's estimator is pretty similar, except that rather than just using the last period before before group S got treated as the baseline, they define the baseline outcome as the average outcome from period 1 to TS minus 1. Because they use more pre-periods, that's the reason why their estimator is more precise and will usually have a lower variance than the estimator of Callaway and Sant'Anna. But at the same time, BJS's estimator could also be more biased if parallel trends does not exactly hold. And Roth 2019 shows actually that with differential trends that tend to widen over time, leveraging earlier pre-treatment periods is going to increase the bias of a diff-in-diff estimator. And accordingly, there could be some kind of bias variance trade-off between those two estimators in instances where parallel trends does not exactly hold. Okay, so finally, let's review estimators that allow for dynamic effects when the treatment is either non-binary or non-staggered. So the ones I want to propose are those that we proposed in a recent paper, again with Xavier. I'm going to describe them when the treatment is binary and non-staggered, but they can be used with discrete treatments or with continuous and staggered treatments. So even when the design is non-staggered, the groups that are untreated at the first period can still be aggregated into cohorts according to the date at which they first received the treatment. Then I'm going to denote by FTT C plus L this average treatment effect here, which is the average effect across all the groups in cohort C of having been treated for the first time L periods ago, relative to having never been treated, and conditional on the treatment trajectories experienced by those groups after the first date where they got treated. In a staggered design, by construction, we would have that all those Ds would be 1. In a non-staggered design, it may be the case that some of those Ds are actually 0 because some groups revert to being untreated thereafter. We show that the diff in diff comparing the C-1 to C plus L outcome evolution of groups in cohort C and in groups untreated from period 1 to C plus L is unbiased for that estimator, for that parameter. That parameter may be hard to interpret because it's aggregating together many different treatment effects, but we show that it can be aggregated into an economically interpretable parameter, which is the cost-benefit ratio that the planner would use to compare groups' actual treatments to the counterfactual status quo scenario where they would have remained untreated throughout the panel. Okay, and I'm already a little bit out of time, so I'm going to skip my conclusion just to say that there are some interesting avenues for future research. This is not like a settled literature yet, far from it. And I'm going to thank you all for coming, and Andrej and Pedro for organizing.
Okay, thank you a lot, Clément, for this great presentation. I will put one question that came in the chat but was not answered. It is from Hazal. Does a time 6 exposure control partially would solve the problem? He was talking about the heterogeneous effects problem that you presented in the first part of the presentation.
So, sorry, could you repeat that?
Does a time 6 exposure control partially solve the problem?
If we were to control, well, I think that's kind of related to the dynamic two-way, the result on dynamic two-way fixed effects regression I've shown. If you instead of just having one dummy for whether you're treated or not, you have like various indicators for how long ago you started receiving the treatment. You may think, oh, that's a much more flexible model that allows for heterogeneous treatment effects. But implicitly, this model is still assuming that those relative time effects are homogeneous, both between groups, but also depending on the calendar time period at which they are realized. So these type of regressions are actually also relying on homogeneous effect assumption and can be misleading if effects are heterogeneous.
Thanks. And I will just put one question and then I propose we move forward. Are the concerns here more general than causal treatment effects? What if just comparing means in crisis episodes with non-crisis without making a treatment effect claim of the crisis? My intuition is that heterogeneity remains a concern, but perhaps not parallel trends.
So, so you would mean if you just want to compare means without making any type of causal claims, right? And you're wondering if, but then if you're not interested in making causal claims, why would there be heterogeneous effects then? So yeah, I think it could be. I think if you're just interested in making descriptive statistics without making any causal statements, probably the issue would not arise. But I would need to think more about it.
Okay, great. Thanks a lot again, Clément, usually we make virtual clap naturally and so on. And I suggest, clap, clap, we move forward to Jonathan Roth. Thanks.
All right, so thanks so much, Andre and Pedro, for inviting me. So the talk I'm going to give today is titled Difference in Differences When Parallel Trends Might Be Violated. As Clément just very nicely summarized, the validity of difference in differences depends on the parallel trends assumption, which says that if the treatment hadn't happened, the mean outcome for the treatment group would have evolved in parallel with the mean outcome for the comparison group. But in empirical practice, we're often unsure ex ante if the parallel trends assumption holds. So we might be worried that there's some time varying confound that affects our treatment group in a different way than it affects our control group. And so there's a very common and very intuitive empirical practice, which is to test for pre-trends, pre-existing differences in trends between the groups as a way of assessing the plausibility of this parallel trends assumption. And so this is a very intuitive sort of partial test of the identification assumptions. But I have a recent body of research describing how, while very intuitive, this type of test has some limitations in the sense that it won't necessarily help us avoid getting biased estimates in all contexts. And so what I'm going to talk about today is first, what are those limitations? And then second, what it is that we can do to address those limitations. And so my talk today will draw on two papers. The first, my pretest with caution paper, which is forthcoming at AR Insights, and then my work with Ashesh Rambachan titled An Honest Approach to Parallel Trends. So the first issue I want to talk about related to pre-trends testing is that pre-trends tests might have low power. So this means that there may be a violation in parallel trends, but because we only have a finite sample, we may not find a statistically significant difference in pre-treatment trends. And so I think that this problem, while a wide-ranging problem, is sort of most easily illustrated with an example. So I have here a plot, which is a very common form of plot in the literature from this paper by He and Wang, who are interested in the impacts of a program that places college graduates as village officials in China. And so what they plot here is, to the left of this vertical dotted line, they have coefficients on leads of treatments. And on the right, they have coefficients on lags of treatment from a two-way fixed effect specification. And so as Clément mentioned, these coefficients are typically interpreted as placebo estimates that should be 0 under parallel trends. And then assuming parallel trends holds, these coefficients are interpreted as dynamic treatment effects estimates. Now, as Clément very nicely summarized, since this is a staggered setting, in order for these to have that interpretation, you need to impose some sort of treatment effect homogeneity across adoption cohorts who adopt at different times. But as I think Pedro will discuss in some of his discussion, the same types of issues will also apply if you use some of these newer heterogeneity robust estimators. But to make things concrete, I'll just go with the original specification from this paper. And so the reason I chose this paper in particular is they have this very nice quote that I think nicely summarizes what is the standard practice in this literature currently. So they write, the estimated coefficients on the leads of treatment, so these 3 pre-treatment coefficients here, are statistically indistinguishable from 0. And we therefore conclude that the pre-treatment trends and the outcomes in both groups are similar. And therefore, villages without the treatment can serve as a suitable control group for villages with the treatment in the treatment period. So because these coefficients are not significant, we're going to interpret these coefficients as valid estimates of the causal effect. So if I could put a little statistical formalism on what I think He and Wang are arguing, they're essentially testing the hypothesis that these 3 estimated coefficients are actually equal to 0. So they're actually equal to these green dots. And indeed, if we did a formal F test of that hypothesis, we'd get a p-value of 0.81. So we indeed cannot reject the null hypothesis that these 3 estimated coefficients are actually equal to these 3 green dots at 0. But the reason that this is not the most compelling argument is that if we test that these three estimated coefficients are actually equal to these three red dots, we would also get a p-value of 0.81. But these three red dots lie on this straight line such that if this were the pre-existing trend and we extrapolated it to the post-treatment period, we would get a bias that's of a similar magnitude as these estimated treatment effects in the post-treatment period. And likewise, if we draw these three blue dots here, we also can't rule out that these three estimated coefficients are equal to the blue dots, but these blue dots are drawn on a smooth quadratic curve such that if we extrapolated that to the post-treatment period, we would get a bias that's of the opposite sign of our estimated coefficients, but of a similar magnitude. And so what I want you to take away from this is that, sorry, my slides froze here. What I want you to take away from this is that, well, it's true, we can't reject the hypothesis of a zero pre-trend. We also can't reject the hypothesis that there is a non-zero pre-existing trend, that if we did some smooth extrapolation of that to the post-treatment period, would produce a substantial bias in our treatment effects estimates. So that's the first issue I want to discuss, which is the low power, potential low power of pre-trends tests. I'm sorry here, my slides somehow are not changing very quickly. Okay, they changed now, great. And so this, of course, was just one example, but in my AER Insights paper, I do a systematic review of recent papers in top economic journals, and I show that similar concerns are very common across a wide range of applications of these types of pre-trends tests. So that's the first issue I want to discuss, low power of pre-trends tests. The second issue, which is a bit more subtle, relates to distortions from pre-testing. So as I just mentioned, when parallel trends is violated, because we don't have perfect power to detect it, we will sometimes fail to find a significant pre-trend. But the draws of the data where this happened are a selected sample from the data generating process. And so if we condition on the draws of the data where we don't find this significant pre-trend, we'll have a form of selection bias, which is known as pretest bias in the literature. And this will introduce additional statistical issues, and as I'll show you, can actually make things potentially worse than if we just hadn't tested at all. So to illustrate that, I'm going to show you some simulations from a very stylized model. So we're going to consider a 3-period model where the treatment occurs for the treated population in the last period. And for simplicity, we're going to assume there's no causal effects of the treatment. But in the population, the treatment group's mean is going to be increasing on a linear trend relative to the control group's mean. And what we're going to observe is the sample means, which for simplicity are going to be the population means plus some independent normal errors. So to visualize that, I have a plot here where on the y-axis, I have the difference between the treatments and the comparison groups in each period. And so in population, this follows this black line where the treatment group mean is increasing relative to the control group mean in a linear fashion. But of course, if we have an actual data set, I apologize, somehow these slides are not transitioning properly. But if we have if we have an actual data set, we of course won't estimate exactly this straight line. We'll have some noisy estimates around the population differences. And so I have here in gray several draws from this data generating process of the realized differences in each period. And so owing to sampling uncertainty, in some of these draws, even though the true difference in the pre-treatment period is non-zero, we're not going to detect a significant trend between period -1 and period 0. So I've highlighted in blue here the draws of the data where this slope is flat, meaning that the change, the difference in differences between -1 and period 0 is close to 0. And so we don't detect a significant pre-treatment coefficient. And so what I want you to notice here is that the way that we don't detect a significant change in the pretreatment period tends to be that we have a negative shock to our estimate for period 0. So these blue dots here tend to be below the population difference in means in period 0. But owing to a mean reversion effect, this means that the slope between 0 and 1, which corresponds with the post-treatment difference in difference effects, actually tends to be very large. So if I average this over 1 million draws, for instance, on average, both of these difference in differences between period -1 and 0 and between 0 and 1 both have an average of 3. But if I look at the draws where things aren't significant, in the pretreatment period, this slope tends to be pretty flat. Here we have on average, it's 1.4, but in the post-treatment period, we have a slope of 3.8. So although there's no break from the trend in the population, in the draws of the data where we find an insignificant pretrend, we tend to see a very flat pretrend in the pretreatment period and a very large treatment effects in the post-treatment period. So to kind of summarize what I've shown you so far, what are the limitations of pretrends testing? The first limitation is our pretest may have low power, meaning that even if parallel trends is violated, we may not find a significant pre-existing trend. And then the second issue relates to the statistical properties of pretesting, where we have the selection bias from only analyzing cases where we find an insignificant pretrend, and that can actually make the bias in the estimates that we actually look at worse. And then a third issue, which I won't go into a lot of detail of, is that sometimes we actually reject the pretrends test, and that's good in the sense that we have a signal from the data that the parallel trends assumption may not hold. But there's then a question of what comes next. We may still want to learn something about the treatment effect. Applied people still need to get tenure. They still need to write papers. And so the pretesting approach is not so clear about what happens if we reject the pretest. So what can we do about these issues? I've sort of proposed two different approaches to dealing with these issues. The first, which is kind of the lower cost approach, is to continue pretesting, but do some diagnostics about the power and the likely distortions from pretesting along the lines of the examples that I've showed you. So if we specify what we think economically relevant violations of parallel trends look like, we can say what are the probabilities that we would find a significant pretrend if that were the true underlying trend, and we can estimate what the distortions from pretesting would be. And so I've developed the pretrends R package and Shiny app, which helps you do power calculations and these calculations of the distortions from pretesting along these lines, so you can try to identify the cases where we think that this pretesting approach will be most problematic. Unfortunately, I won't have time to delve into a lot of the details of how that works, but I will discuss in a little bit more detail an alternative approach, which I developed in this paper with Ashesh Rambachan, where we developed formal sensitivity analysis that formalizes a lot of the intuition underlying pretrends testing, but doesn't actually rely on a pretest step per se. So in the remaining few minutes that I have, let me just tell you a little bit about how that approach works. So the observation that motivates this paper is that the intuition behind pretrends testing is that the pretreatment difference in trends are informative about the counterfactual post-treatment difference in trends. And so we're going to formalize this by imposing restrictions that intuitively say that the counterfactual difference in trends can't be too different from the observed true pretrends in the data. And so if we have restrictions that the true pretrends can't be too different from the counterfactual difference in pretrends, this allows us to place bounds on the treatment effects and to construct valid confidence intervals so long as our imposed restrictions are correct. And so this approach nicely enables sensitivity analyses where we ask how different would the counterfactual difference in trends have to be from the pretrends in order to negate a particular conclusion, say that we have a significant positive effect. Sorry about these slides here.
What is?
Okay. So just to give you a little bit more detail on what these types of restrictions look like. So if we consider our 3-period model from before, and we denote by delta 1 to be the true violation of parallel trends, so the true difference in trends between period 1 and period 0, well, that's the bias of our estimator. Unfortunately, we can't directly identify delta 1 because we don't observe the untreated potential outcomes for the treated group. But we can identify its pretreatment analog delta -1, which instead of comparing period 0 to period 1, compares period 0 to period -1. And so intuitively, what we're going to do is we're going to say, if we knew the true pretreatment difference in trends delta -1, we could use that to bound the range of the possible values of delta 1. So we're going to say intuitively that the true post-treatment difference in trends can't be too different from the true pretreatment difference in trends. So what types of restrictions might be reasonable relating delta 1 to delta -1? So one type of restriction we think might be reasonable in a lot of contexts is to bound the relative magnitudes of these differences in trends. So we could require, for instance, that delta 1, the post-treatment difference in trends, could be no more than some constant m bar times delta -1, the pretreatment difference in trends. We likewise can impose smoothness restrictions, so we can say, if we take this pretreatment difference in trends that's identified and we extrapolate it, that maybe this post-treatment difference in trends wouldn't lie too far from this linear extrapolation of the pretreatment difference in trends. And in the paper, we talk about a lot of other different types of restrictions that might be reasonable in a variety of contexts, depending on what you know about how parallel trends might be violated. So let me just now show you how this type of approach can be used in an application. So we're going to think about an application to this paper by Benzardi and Carloni, who study the incidence of a cut in the value-added tax on restaurants in France, which occurred in 2009. And so this is going to be a very simple, non-staggered difference in differences, where they're going to compare restaurants who are affected by this tax change to other firms in different sectors that aren't affected by the tax change. And they're going to look at the effects on firm profits of this change in tax. And so here we have the event study for this paper, where log profits is the outcome. And so these 4 coefficients here are the pretreatment differences in trends. And you can actually reject that these are all exactly equal to 0. So this coefficient in 2007 is statistically significantly different from 0. And these are actually jointly statistically significantly different from 0. But it does kind of look, if you look at the plot, like the changes in the post-treatment period are larger than anything that we've seen in terms of differences in trends in the post-treatment period. And so we can sort of formalize that argument, where here what I have is a sensitivity analysis plot, where in blue I have the original confidence intervals from their results for the effect in the first year after the reform. And then what I have in red is I have robust confidence sets using our approach, where we allow for the difference in trends to be no more than m bar times the maximal pretreatment difference in trends. So m bar equals 1 says there can be differences in trends in the post-treatment period, but they can be no larger than the max difference in the pretreatment period. And so what we see here with m bar equals 1, we can still rule out that there's 0 effects on profits. But if we start allowing the difference in trends in the post-treatment period to be larger than the maximum in the pretreatment period, then our confidence sets get wider. And at around a factor of 2, we can no longer rule out a 0 effect. So this says, roughly speaking, that we can rule out a null effect unless we allow for violations of parallel trends that are about 2 times larger than the maximal violation of parallel trends in the pretreatment period. So I think I'm out of time. So just to kind of wrap up, tests of pretreatment differences in trends, or pre-trends, are an intuitive test of the identification assumptions in difference and differences, but they're not a cure for everything. And in particular, they may suffer from low power and introduce additional biases from pre-testing. And so the 2 papers that I talked about today provide tools for one, diagnosing when this is a problem, and two, doing formal sensitivity analyses that try to formalize some of the intuition behind pre-trans testing. So thanks very much for listening.
Thank you. Thanks a lot, John. Great. Actually, and we have a few questions before we continue with Brantly. So there is a general question that I would leave for the end about comparison with synthetic control methods. I'm sure we will address it, but there is firstly a question from Daniel Kleinenberg. With regards to pre-trans package, how do you interpret when the metrics don't agree? For example, suppose someone uses your package comparing the recommended linear alternative as in the package example, and the results say the test has a power of 80%, the base factor is small, like 0.3, but the LRT has a massive test statistics, like greater than 20. Thanks.
Yeah, good question. So when we talk about power of pre-trans tests, I think it's important to distinguish between two measures of power. So there's ex ante power and ex post power. So ex ante measures of power say, if I know the precision of your estimates, but I don't actually know what the estimates are, how likely would I be to detect some difference in trends if that were the true difference in trends? And then ex post measures of power say, now that I know your estimates, what differences in trends can I rule out or not at what levels of significance? And so ex post measures of power incorporate more information in the sense they're telling us what can we rule out. On the other hand, relying on ex post measures of power sort of introduces additional publication bias type of issues where if depending on the noise in your data, you may be able to rule out some things or not rule out some things. And so if you sort of want to control, average power in published studies or something like that, you actually, the thing to focus on is ex ante measures of power. So there's sort of, pros and cons of different measures of power. And so the different criteria that you mentioned, Andre, that the package reports, the sort of power of 0.8, I think you mentioned, corresponds with the ex ante measure of power. How likely would you be to detect this difference in trends given the precision of your estimates? And things like the likelihood ratio are ex post measures of power. They say, given the observed data, how likely would it be that we observe this difference, the hypothesized difference in trends relative to a zero difference in trends?
Okay, thanks. I hope this was sufficiently answered. And due to time, I just posed one very short question. It was also in the chat. I believe the packages you mentioned were in R. Are there also packages from your work in Stata?
Not yet. If anyone is interested in helping with converting things to Stata, we're very open to that. The pre-trans package does have a Shiny app, which you can use online. And so you just upload a CSV of your estimate. So it's pretty easy to sort of export from Stata to the Shiny app if you're interested in that.
Great, thanks. Thanks again. Thanks a lot for the presentation. And we continue again with Brantly Callaway. Please. Hope everything will work. I think, John, that you have to assign to Brantly the host rights. I will just do this myself. Oh, it's okay. Great. It should work now.
Okay, can you see that okay?
Yes.
Okay, good. Andre, thanks a lot for having me. It's good to be here. My name's Brantly Callaway. This is joint work with Andrew Goodman-Bacon and Pedro Sant'Anna about differences with a continuous treatment. So starting out, it's good to come after Clément here because I can skip a lot of the motivation and setup here. But let me just kind of remind you of a few things that he already said, but that will connect to what we're doing in this paper. So I think this is painting with extremely broad strokes, but I think if you think about what's been happening in the literature on differences lately, I think you can broadly classify a lot of these contributions as being in two categories. One being about diagnosing issues with two-way fixed effects regressions. I think these were the first half of Clément's presentation. And if you summarize those issues in really just 2 bullet points, in the case with the binary treatment, I think the key issues are that one, already treated units can sometimes serve as a comparison group. And in a world with heterogeneous treatment effects, what this means is that when treatment effects can vary across units, and in particular when they're treatment effect dynamics, so that the effect of participating in the treatment can vary with length of exposure to the treatment, that you can get very poor estimates of causal effect parameters in that case, the negative weighting problem that was pointed out earlier. And then the second part here is that if you do two-way fixed effects regressions, in as much as you think about beta from this two-way fixed effects regression corresponding to a weighted average of underlying treatment effect parameters, the weights on those underlying treatment effect parameters are driven by the estimation method. Now, in a world, so if treatment effects are homogeneous, so if the effect of participating in the treatment is the same for everyone, these weights are generally pretty good. Under some extra conditions, you get efficient estimators this way. But in a world with heterogeneous effects, the case for those sort of weights being driven by the estimation method becomes substantially weaker. And then the second strand of this literature, which also includes pretty much all of the first papers that I mentioned, but some additional papers as well, have proposed ways to fix the issues that show up with two-way fixed effects regressions. And basically, I think all of these papers have more or less the same idea in terms of the negative weights. To solve those sorts of problems by explicitly making good comparisons. So compare units that become treated to units that aren't treated yet, and to explicitly not make the bad comparisons, not make the comparisons that lead to negative weights and two-way fixed effects regressions, to explicitly not make comparisons that involve units that become treated to units that were treated, that are already treated. And the second part of these fixes is to choose your own weight. So if you're interested in, say, some kind of overall ATT type parameter, an overall average treatment effect parameter, choose weights that are targeted towards recovering that parameter. Or if you're interested in an event study, so for example, reporting how the effect of participating in the treatment varies with length of exposure to the treatment, choose weights that target event study sorts of parameters. Or if you're interested in some other kind of causal effect, choose weights on your own that explicitly target the parameters that you're interested in. And so, like Clément said, most of that literature, with a few exceptions, mainly his work, but most of that literature is focused on the case with a binary staggered treatment. So binary treatment meaning that individuals either participate in the treatment or don't, and staggered meaning that once you become treated, once a unit becomes treated, they remain treated in the following time periods. Now, of course, at least in my view, I think this is a leading case and a case that it makes sense that the literature has started out thinking about, but it's certainly not the only case. And there seems to be a lot of demand for understanding difference and differences type arguments and how they relate to more general treatment regimes. My co-author Andrew Goodman-Bacon made this slide about people tweeting about wanting results that are this type of results that have been showing up in the binary staggered treatment adoption case, but for more general sorts of treatment regimes. And we're going to do a version of that in this paper. So there are ways you can generalize binary and staggered adoption. The way we're going to generalize it in the current paper is that instead of thinking about the case with a binary treatment, we're going to think about the case with a multi-valued or a continuous treatment. Throughout the talk, I may sometimes say the word dose. If I slip into saying the word dose, I mean the same thing as continuous treatment. And to be a little bit more specific about what we're thinking about, is we're thinking about the case where researchers have traditionally estimated this kind of two-way fixed effects regression. Here, Y is some outcome, theta is a time fixed effect, eta is an individual fixed effect. DI is the amount of treatment that unit I experiences. Treat is a dummy variable indicating whether or not they participate in the treatment. And here the parameter of interest would be beta, beta with a superscript TWFE standing for two-way fixed effects. And this would typically be interpreted in applications, sometimes loosely interpreted, as something like an average causal response parameter, something like how much the causal effect of a marginal increase in the dose on the outcome of interest. Well, so most of our identification results that I'll show you as I go through the talk, they'll apply for if you have a binary treatment or a multi-valued or a continuous treatment. Some of the results, I'll show you some results about interpreting two-way fixed effects regressions, and they'll apply to the case either where the treatment is continuous enough that researchers would run this sort of regression instead of including maybe a sequence of dummy variables, or an actually continuous treatment. Okay, and I'm going to take a couple of slides and tell you kind of what the main results of our paper are, and then in as much time as I have left, I'll go into the details of what I think are the most important details from our paper. So first of all, if you think about two-way fixed effects regressions that most researchers are running in this sort of setup where they have a multi-valued or a continuous treatment, so probably not surprisingly, if you're in a world with multiple periods and variation in treatment timing and heterogeneous treatment effects, this is a more complicated setup than the case with a binary treatment. And so probably not surprisingly, a lot of the same issues, as well as some new issues, come up in this case. And in particular, already treated units can serve as a comparison group. This means in the presence of treatment effect dynamics, this can lead to, I'll just say here, poor estimates of causal effect parameters of interest. Second, like the case with the binary treatment, beta from this two-way fixed effects regression, it delivers a weighted average of some underlying treatment effect parameters, and the weights are again driven by the estimation method, perhaps undesirably driven by the estimation method. And then a new one here that maybe I'll explain later on in the talk, but is about the case where there are heterogeneous causal effects, meaning that the effect of more dose can vary across timing groups, so groups that become treated at different points in time. In that case, that can also be a source of poor estimates due to negative weights in this case. As in the case with the staggered binary treatment, we can fix all of these issues, and the fixes can be the same as in the previous case. So carefully make desirable comparisons, make comparisons between units that become treated relative to units that don't participate in the treatment yet, and explicitly don't make bad comparisons where the comparison group involves already treated units. And second, using the same second strategy of choosing our own weights that are directly targeting treatment effect parameters of interest. So all of that, I think this slide is maybe a good news slide. The next slide is a bad news slide. And in particular, what happens when you move from a world with just a binary treatment to a world with a multi-valued or a continuous treatment, it introduces new issues. And these are both conceptually different from the sorts of issues that show up in the case of the binary treatment. And I think they're, at least to me, they seem fundamentally more challenging than the sorts of issues that show up in the case of the binary treatment. I'll move into the details of this is the main part of what I talk about today, but let me give you the intuition for this. So if you think about standard versions of difference and differences, standard versions of parallel trends, assumptions, underlying difference and differences approaches, these approaches, they deliver ATT type parameters, so average treatment effect on the treated type parameters. This happens even in the case where the treatment is binary. But what ATT type parameters are, they're local sorts of parameters. Even in the case when you have a binary treatment, they're local parameters that are local to the group that participates in the treatment. But in the case where you have a multi-valued or a continuous treatment, if you want to make comparisons across different amounts of the treatment, these sorts of comparisons are going to be, and interpret them causally, those sorts of comparisons are going to be hard to justify under standard parallel trends assumptions. And the intuition for that is that standard versions of difference and differences, they deliver local treatment effect parameters, and that local treatment effect parameters are inherently hard to compare to each other. And that in particular, if you want to make these sort of comparisons, they partially involve a causal effect of more dose, but they also involve something that looks like a selection bias sort of term. And so any sort of comparison between local treatment effects across different values of the dose. There are competing explanations. There's one explanation that the differences are an actual causal effect, and another explanation related to selection bias, and standard parallel trends assumptions alone aren't enough to distinguish between either one of those theories or combinations of those explanations for the differences across treatment effects across different amounts of the dose. And in particular, if you want to get rid of these sort of selection bias type terms, fundamentally it seems to likely that it's going to require some kind of additional assumptions that are likely to be substantially stronger in practice and likely to be substantially stronger than what most applications in economics and in other fields probably think that they're making. Okay, so here's the outline of the talk. So since I don't have very much time, I think our most interesting results I can show you in a baseline case where they're basically a textbook case where there are 2 time periods. No one's treated in the first time period. Some units become treated in the second time period. Some remain untreated. This is exactly the same as you'd read in a textbook version of difference and differences. The only difference is that I'm going to allow for the treatment to be either multi-valued or continuous instead of binary. I'll also show you what happens to two-way fixed effects regressions in that case. And then I think I'll just show you one slide about what happens in more general cases where you have multiple time periods and variation treatment time. You'll see the main intuition for what we're saying here in the first bullet point. Okay, so here's a notation that I'll use. I guess maybe in this sort of thing, we've not converged on sort of a unified notation. So my notation I hope will be easy to follow, but it is slightly different than in the last 2 slides. Here, I'm going to have 2 time periods. I'm going to call them T star and T star minus 1. No, T star minus 1, maybe I'll say is the first time period, refer to it as the first time period. No one's going to be treated in the first time period, and then some units become treated in the second time period. In the second time period, so we'll define potential outcomes. This is the outcome unit I would experience in the second time period under some particular amount of the dose. This gives us a way to think about what outcomes would have been under different doses for that particular individual or unit. And then in terms of observed outcomes in the second time period, the observed outcome will be the potential outcome corresponding to the actual amount of dose that that unit experienced. And in the first time period, we observe untreated potential outcomes for all units. In the case where so compared to the case where you have a binary treatment, the number of treatment effect parameters that you could be interested in when you have a multi-valued or a continuous treatment, there are more potential parameters that you could be interested in. Probably the one that's most analogous to the case of the binary treatment is what we call in the paper a level effect. This is the average treatment effect on the treated. It's the difference between potential outcomes under dose D relative to untreated potential outcomes. It's on average, and it's among those that actually experience dose D. And I think this is the natural analog of the case with the binary treatment. If the only value that D can take is 1, this corresponds to the average treatment effect on the treated in the case in the binary treatment literature. That said, when you have a continuous treatment, you could think about one thing that might be desirable to do would be to take derivatives of this ATT function. So here, we call this a slope effect or a derivative effect, which is a derivative of this ATT function. And this is how much the ATT changes for those that actually experience dose D under a small increase amount of the amount of the dose they experience. Both of these, so this ACRT and this ATT, these are both in some sense functional parameters. So probably you can see these as a function of the dose. And I think many applications would plot these as a function of the dose. If you want something that's just one number, so if you think about beta from a two-way fixed effects regression, it's just a single number. The natural way to aggregate this into an overall average causal response, which is probably the natural target parameter for beta in a two-way fixed effects regression, is to just average this thing over the distribution of the dose. This overall average causal response is a single number, single summary measure of the average causal response. You could, I'll probably skip this in the interest of time, but you could do similar things if you have a discrete dose. You can think about a level effect. Instead of taking derivatives, you can think about slope effects that are just effects of the nearest dose relative to the previous dose. In the last few minutes here, I'll just talk about the case with a continuous dose. What standard parallel trends looks like, if you're familiar with the literature on binary treatment, is this. It says that the path of untreated potential outcomes, so this is the change in untreated potential outcomes over time among those that experienced dose D, is equal to the path of untreated potential outcomes among those that were untreated. What's different here, we don't see this path of untreated potential outcomes for the group that experienced dose D, but we do see the path of untreated potential outcomes for the untreated group. And if you walk through these same sort of steps as would show up in the case with the binary treatment, you can recover the ATT of dose D, which is equal to the average change in outcomes experienced by those among those that experienced dose D relative to the average change in outcomes among those that were untreated. This is exactly like the case with the binary treatment, except that D can take on different multiple values, perhaps. And this is exactly what you would expect here. The question might arise, like ATT of dose D, it's an interesting causal effect parameter. In the case with the binary treatment, that pretty much ends the identification argument for ATT. I think in the case with the multi-valued or continuous treatment, though, there are more interesting things that you might want to do. And in particular, you might want to compare ATTs across different values of the dose. And besides that, you might want to say you plot ATT as a function of the dose. At a minimum, it's very tempting. Say you see this as increasing, ATTs are increasing as a function of the dose, to say that more dose causally increases outcomes relative to less dose. And that's the sort of comparison that we zoom in on as being potentially problematic. And then besides that, if you think about derivative sorts of parameters, which remember beta from a 2 fixed effects regression is at least interpreted as a derivative of a causal response function. Derivatives inherently involve local comparisons, comparisons between doses that are just very close to each other. And so let me, in my last few minutes here, I'll take maybe 2 or 3 more minutes here, if that's okay, Andre. Let me show you what happens if you try to compare ATTs across different doses. So here, I'm going to use the notation. This can be any doses that you want. I'm going to call these DH and DL, just so I can say the words high dose and low dose, but they can be any doses that you want. If you take just a few lines of algebra here, you can see that this decomposes into, so this first term is the difference between potential outcomes under the high dose relative to potential outcomes under the low dose among the high dose group, among those that experience a high dose. This is a causal response sort of parameter. This is how much outcomes causally increase due to different amounts of the dose. That's something we would like to have here. But there's this leftover term. This is a difference between the ATT of the low dose. So this is an ATT of the low dose here and an ATT of the low dose here, but they're conditional on those that experience the high dose relative to those that experience the low dose. And standard parallel trends assumptions have nothing to say about this, have nothing to say about different ATTs for the same dose among different groups. And in particular, something like the high dose group, something like a case where the high dose group experiences larger ATTs at all doses would mean that this term is not equal to 0. And that would mean that comparisons across different doses involve a causal response plus a non-negligible selection bias sort of term. And then this sort of thing, if you take doses that are right next to each other, this sort of thing spills over into ACRT, so into derivative types of parameters. Now, what we point out in the paper is if instead of targeting a local parameter, if you target a global parameter, so here, this is an ATE parameter. I won't go into detail here, but the difference is that we don't condition on the actual amount of dose experience. If you target a global parameter like this, then differences across ATEs, across doses, you can interpret them causally, but in order to get something that's a global type of parameter, you need to make stronger assumptions, potentially much stronger assumptions than what you need in order to recover a local ATT type parameter. And so that's probably one of our main contributions. Let me show you one last slide here about 2-way fixed effects regressions. So if you do 2-way fixed effects regressions, this is still in the simple case with a with 2 time periods. Even in this case, under this standard version of parallel trends, what you get is a weighted average of something that's a causal response parameter plus something this is a selection bias type term here. So you get weighted averages of things that are causal responses, but also include selection bias. So in order, that I think inherently makes beta from these kind of two-way fixed effects regressions hard to interpret. And in order to get rid of those sorts of selection bias type terms, I didn't say what strong parallel trends is, but it's a stronger assumption that's related to parallel trends assumptions. If you want to get rid of selection bias type terms, it would seem to inherently require making stronger assumptions than just regular old parallel trends to get rid of those things. I don't have any more time. I think Pedro may mention this in his slides. The weights here can also be weird. So they're all positive, but all positive weights, I think it's sometimes cited in the literature as being a requirement for reasonable weights on underlying treatment effect parameters, which I agree with, but it's a very minimal sort of requirement. And here the weights can be quite weird. We have the basically a preliminary version of an application, and in the application it makes a very big difference. The weights driven by the distribution of the dose itself relative to the two-way fixed effects weights lead to much different sort of estimates of summary causal response parameters. Okay, I'll stop there. I'll just put up my conclusions slide. Here's a link to the paper. If you want kind of user-friendly sort of summaries, there's one on my website, one on Pedro's Twitter. I'm also very happy to get comments through my email. And I guess this project is quite new, so we don't have kind of code quite yet that you can download and use, but I expect that to be available over the next few months. Thanks a lot.
Great, thank you. Thanks a lot, also Brent, for a great presentation. Just a second. Great. So we have quite a few questions, but I will just ask one that came. First, which of those methods are suitable to a case where people get treated for a certain period and then they switch over to non-treatment? For example, in a 5-period treatment scheme where others get treated in periods 2, 3, and then they quit in periods 4 and 5. Thank you. Which of the methods?
Yeah, so I think there are actually a lot of methods that can work for this. So like in our case, we've usually defined things by groups, where group corresponds to the time period when a unit becomes treated. But if you have more complicated treatment regimes, like people moving into and out of treatment, you can at least identify some causal effect parameters by defining more complicated groups. So like you can define the group by the entire path of moving into and out of the treatment. My sense is that sometimes that there can be a curse of dimensionality if you do this. So like if there are lots of different paths into and out of the treatment, that estimating things may become perhaps substantially more complicated. But at least from an identification standpoint, my sense is that a lot of the arguments are pretty similar. Clément actually has the paper that's a paper that addresses this, I think, very, very clearly. So you could look up his paper. He has, I would give you the, I think it's 2021 paper, but I think he has multiple 2021 papers. But you could probably get that from him in the comments where to look there. Also, these imputation estimators, I think, kind of go naturally in this case too, that you can pick up kind of an imputation of untreated potential outcomes and then compare that to observed outcomes, allowing for different sort of treatment paths.
Okay, thanks. And there are also questions for that you put links in the chat, Brantly. So
yes, definitely will do that.
Yes, thank you again. Big clap for a great presentation. And we continue with Lihua Lei, your presentation.
Great. Can you see my screen?
Yes.
Yeah. All right. So thanks for having me in the seminar. And it's my great pleasure to share one of my very recent work on two-way fixed effect regression estimators. And today I'm going to show you a perhaps very surprising property of the two-way estimator. And this is a joint work with my amazing collaborators, Dimitri, Hido, and Shelma. So this has been popped up again and again, but let me just have a quick intro of this. So we have this two-way model, which is basically decomposing the outcome into the unit fixed effect, time fixed effect, the treatment part, and the covariate part, and also a stochastic error. And then this motivates the two-way estimator by running the least square on that. So what we know is when there are only 2 time periods, and if those units only get treated in the second time period, then this is equivalent to the DID estimator. And that's probably why it starts to be so popular for a few decades. And what we know is this estimator is unbiased for this tau, for this coefficient, if the two-way model is correct. But of course, as you can see from the recent soaring literature, this estimator is not very good because it's biased if you have heterogeneous treatment effect or a violation of parallel trend. And of course, in the literature, people are not stopping there, and they propose so many great alternative methods. So here I just name a few, but you can definitely expand the list infinitely. But a main question for us is that, given so many papers around this topic, has this two-way fixed effect estimator been fully understood? And the answer is no. So in this talk, it basically has 4 parts. So the first one is we will define a class of estimates called W average treatment effect, or DATE in short. And this type of estimate is more like ATE rather than ATT that's usually mentioned in the literature. And then that comes the most surprising part. So we want to ask what design of experiment that can justify the two-way fixed effect estimator, in the sense that the two-way estimator will converge to DATE. Turns out there's something called DATE equation, which hopefully I will tell you in a moment and convince you that this is something really unexpected. And after that, but the first 2 points are just about randomized experiment. But in many cases, we don't have that. We don't have that flexibility to design our own experiment. So instead, in the general design-based inference, we generalize this estimator, the two-way estimator, to what we call the reshaped IPW estimator, which is valid without any parallel trend and allows for almost arbitrarily time and unit varying effect. And moreover, it works for many practical designs, meaning that you can sample without replacement, you can do class-wise randomization, etc. And finally, this estimator is shown to be doubly robust in the sense that it will converge to DATE if either the treatment assignment model is null or well estimated, or the two-way model is correct. So let me start with the first part. So here we consider a setting where we have a balance panel with n units and t time periods. So in this work, we consider a case of a fixed t. So it turns out a fixed t case is much harder than large t case, which I will discuss later. So this may sound a little bit weird, but I will explain that later. And then we consider the special case where we have a binary treatment. And we use this bold WI to denote the treatment path. And I apologize, I'm not using D or T here, I'm using W. For each unit and each time period, we will consider the potential outcome written as YIT1 and YIT0. So we know that when we write this down, we assume a weighted dynamics, because in principle, each potential outcome depends on both the past and future treatment assignment. But here, we assume it only depends on the contemporaneous treatment. But other than that, we can allow this potential outcomes to be either fixed or random. And in the first 2 parts of the talk, I would treat it as fixed. And we will not assume any parallel trend. And we will assume that the effect, meaning that YIT1, YIT0, can be arbitrarily varying with time and units. And our causal estimate, DATE, is basically an average of this individual treatment effect. So it's just like the cross-sectional case. But here, because we have 2 dimensions, time and unit, so what we're going to do is we first average over units for each time period. And then we will consider a weighted average with a user-specified weight. So this is very important. So these weights are not driven by the data. It's defined by the user. So in particular, just for simplicity, in the interest of time, we will consider date with equal time weights, which is essentially the unweighted average of everything. So then let's consider this problem. So suppose we are a RCT designer. And for most panel data, because you have multiple time periods, even if you have a binary treatment, you cannot run all 2 to the possible treatment assignments. So usually, if you want to design RCT, you have to restrict yourselves into a subset of possible assignments. So for example, if you want to run an experiment with staggered adoption, then you reduce 2 to the t to t plus 1. So here, let's say this S design is your restriction. And then for this RCT designer, her goal is to design a distribution on this subset. And then given n units, she will assign the treatment path to each unit independently. And after getting this treatment assignment, you will see the outcomes. So you will get the data. And then she will pass the data to a data analyst. And let's assume that this data analyst is going to use two-way estimator to analyze the data. So now the question is, what design, or is there any design that can guarantee that the two-way estimator is consistent for date? Well, an educational guess is that uniform design. Because in the cross-sectional case, we know that if we can run a uniform design, like half and half for the treaty and control, that would be one of the most ideal things to do. But perhaps surprisingly, this is not always true. So let me give you 2 very concrete and simple examples. So here, consider 3 time periods. And there are 2 types of restrictions. One is what we call transient design, in which everybody is either never treated or get 1 period to be treated. So this can happen in things like marketing, where during a period of time, each user will be given exactly 1 coupon at some point. And another example would be the well-known staggered adoption design. So for both designs, you see that there are 4 types of possible assignments. So turns out, all designs that guarantee the two-way estimator to converge to date are given by this. So let me go through this slowly. So you see that a design is a distribution on these 4 elements. So in other words, a design is just 4 numbers. So it turns out for the transient design, these 4 numbers can be anything as a convex combination of these 2 vectors, where the first one is putting all mass on never treated. And the second one is putting no mass on never treated, but putting equal mass for the remaining 3. But of course, you don't want any treatment assignment to have 0 probability. So then you take the convex combination. So again, these vectors are not important. So the only takeaway message here is that the uniform design is indeed a solution. So in other words, if you run a uniform design, then your two-way estimator will converge to the date. But for staggered adoption, things go wild. So it turns out these 4 numbers will be a convex combination of these 2 vectors with those magical numbers. And this will be the only solutions if you don't restrict your heterogeneity of the treatment effect. And one takeaway message from here is that the uniform design is no longer a solution. So when I first saw this, I thought I must do something wrong. And then I ran a simulation. And hopefully after this, I convinced myself this is not something wrong. So here I generate a simulation setting, and the details are not important at all. So the only thing is here we have this data, and then we run this uniform design in these 2 cases, and then we run another design, which is one of the solutions for the staggered adoption in the last slide. So you can see here that if you run the uniform design, the staggered adoption, for staggered adoption design, the two-way estimator is biased. But for transient, it is unbiased. But for the other one, it's the opposite. So it exactly reflects what I just talked about. So what's this magical numbers? So it turns out the underlying thing is what we call data equation, which is given in this equation, which looks a little bit complicated. But again, the math is not important. So let me just explain what roughly it means. So here, suppose we're given this restriction, this subset of possible assignment. And what we can show is, without any other restriction on those potential outcomes, the two-way estimator converges to date if and only if this equation holds. And the thing is, this equation only depends on this S design. So it's really a design equation. Okay? So you don't need to see the data before determining this, this capital pi, this design. And moreover, mathematically, it's a set of quadratic equations with some linear constraint, because this pi is a distribution. So all the entries should be positive. But in principle, we know that there might be infinite solutions or no solutions for a quadratic system. But turns out, fortunately, for most existing examples like DID, crossover, staggered adoption, transient designs, we derive the closed form solutions. And moreover, if you do have some designs that beyond this, we also have a generic solver based on nonlinear programming. So we turn this equations into an optimization problem. So that's about data equation. And the next question would be, what if you don't have an idealized experiment? So in this case, just to make it more formal, suppose you are in a case where your treatment paths are drawn randomly, but each of them has a different distribution, say pi I, and this pi I differs across units. Then how are we going to apply the results I just stated? So a simple idea is just to shift your data to an ideal randomized experiment using a weighted two-way regression estimator. So in particular, the RIPW estimator is defined in the following way. So here you see, this is the least square objective function for two-way estimator. But on top of that, we add a weight, which looks like the inverse propensity weighting. But it's not exactly that, because in the numerator, there is something we call the reshaped distribution, which is the solution of the data equation. So you see that if the uniform distribution is a solution, then this goes back to the IPW estimator. But for things like staggered adoption, we know the uniform distribution is not a solution. So here, we're going to reshape our IP weights. And one more thing is, if we're indeed in an idealized experiment where all this pi I, all the treatment paths are generated from the ideal experiment, then this weight equals to 1. So you go back to the standard two-way estimator. So this is a strict generalization of I just talked about in the first bar. And just one slide summarizing what we have. So in this case, what we can show is, first, this RIPW estimator will converge to date under my assumptions. And basically, we just need overlap, limited dependence, and some bounding moment for the potential outcomes. So here, we don't need parallel trend of any kind. We don't need any homogeneity among those treatment effects. And moreover, we propose a conservative variance estimator and a valid confidence interval under a wide class of designs. And this includes like Bernoulli design, where WIs are independent, or sampling without replacement, or class-wise randomization, or two-stage randomization. So this is very important because in practice, it's very rare that you are running this Bernoulli design. So roughly speaking, we have a master theorem showing that if you have a way to handle a particular design in the cross-sectional case, then you can bring that into this problem. So that's why we can cover so many designs. Okay, so that's the second part. And then it's about double robustness. So here, in order to talk about double robustness, we need to introduce covariance because that will make the things more interesting. And here we consider this both phase xi as a generic covariant. So it could be either be a time invariant predictor, which is just the same for every time period, or it could be time variant predictors, but we compile them into one symbol. So the only requirement is that it satisfies a latent ignorability assumption, which is quite technical. But roughly speaking, if you have this time invariant thing, then it will be satisfied in many cases. Or if you have time varying things and the covariates are strictly exogenous, then you will also satisfy this assumption. But this assumption is even more general than what I just told you. So if you're interested, you can go into our paper. And what we are going to do is we first use this covariate to fit a assignment model. So if you have staggered adoption, you can fit a duration model because you can treat the time that this unit gets treated as a, say, survival time or event time. So you can fit something like Cox model, which I'll give an example later on. And for general designs, when the unit is allowed to switch on and off in terms of the treatment assignment, then you can fit things like Markov model or conditional logic model. So on the other hand, we can also use this covariate to fit an outcome model. But we only need to capture the effect that varying with both unit and time. So let me explain this. So for example, suppose you're fitting a standard two-way model using X, and then this term, which vary with both I and T, other than this two-way fixed effect, is usually characterized as a linear transform of your covariates. So then we only need to get this beta hat. And this is very important in our setting because if you have this model, but if your T, the number of time period is fixed, then this unit fixed effect can never be consistently estimated. So in other words, if you require the whole outcome model to be consistently estimated, it's unrealistic. But here we don't need that. So that's why here I say a fixed T setting is much harder than a growing T setting. Because when you have a large number of time period, at least you can estimate the unit fixed effect consistently, but here you can't. So once you have this component, what you can do is you first do a regression adjustment to turn this outcome into a modified outcome. And then you pretend that your estimated propensity score is the true one. And then you run RIPW estimator. So it's a two-stage procedure where in the first stage, you estimate the outcome model and treatment model, and then you do the standard thing without covariate. So then what we can show is this estimator is doubly robust if either the assignment model is well estimated or the two-way model is correct. So the intuition is very simple. If the assignment model is roughly correct, then this goes back to our design-based theory and everything works. And if the two-way model is correct, then this least square objective is basically capturing the correct model. So you are running a weighted ORS for a linear model. And as long as the weights behaves reasonably well, you will have consistent estimate. And moreover, this is not just for point estimate, because inference is so important. We also derive doubly robust confidence interval by cross-fitting those nuisance parameters. And one thing is, there are two notions of double robustness in the literature. One is the weak one, says that the estimator is consistent if either model is well estimated. But here, our double robustness is even stronger than that, saying that on top of that, we can achieve a smaller error if both models are well estimated. Okay, so in the last part, I will give you a short case study. So I guess I will have 5 minutes, is that right?
Yes.
Okay,
but please feel free. Yes.
Yeah. So here, this is the problem we study, which we find very cute. So you may still have the memory of what happened last year if you are in the US, but I mean, everyone in the world will have a version of this. So in the US, basically everything turns virtual after late February or early March because of the state of emergency. So starting from February 29th, the state of Washington first announced this state of emergency, and everything turned virtual in the next 20 days. So our interest is to study the effect of the state of emergency, this extreme government action on the public. And of course, this is a very short-range thing, short-term thing. So it's very hard to measure the economic activities. But interestingly, this open table app which is an app for table reservation in restaurant, released the data in early pandemic. And in particular, it provides daily data of year-over-year city diners for a sample of restaurants in 36 states in the United States. So then we can take that as our outcome variable. And we're interested in the short-term effect of state of emergency on the economic activities measured by this dining rate. So as we know that there are thousands of papers during the pandemic on policy evaluation, we know it's super challenging. There are a lot of things that are debatable, but this problem is a little bit special because this is basically the first policy affecting the vast majority of the public. So compared to the later ones like mask mandate or lockdowns, it was much less confounded. And meanwhile, the restaurant industry is responding to the policy very swiftly. So it is thus immune to some long-term confounders. So I'm not saying this problem is easy. It's just relatively easier than other problems. And another important feature of this problem is that the declaration time is easier to model than the dining rate, because the dining rate is driven by a lot of unmeasured behavioral variables. But declaration time is mainly driven by two things. One is the progress of the pandemic. The other one is the authorities' attitude. So here, just for demonstration, so I'm not saying this is a very good analysis. This is just demonstrating how to use our estimator. We consider three covariates, which are the accumulated confirmed cases, which measures the progress, and then the vote share of Democrats based on the 2016 presidential election, which measures the attitude. And then it's the number of hospital beds per capita, which measures the amount of medical resources. And then what we are doing is for assignment, we fix a Cox model. And for regression adjustment, we fit a standard unweighted two-way model. And then our RIPW estimate is about -4%, which is significant at level 90%. But the unweighted two-way estimator is much smaller than that. So again, take this with a grain of thought. We're not claiming that this is a very good analysis, but hopefully this demonstrates why our estimator is useful. So just to wrap up, in this talk, we proposed a date equation that identifies all randomization schemes for which two-way estimator converge to date. And then we generalize that to RIPW estimators that permits valid design-based inference for most practical designs. It's not just for limited to staggered adoption. And then they're double robust and work for general designs. And practically, they empower the users to leverage the information from the assignment models. And that is an actual source of information. And also, because it's just a weighted two-way estimator, so it can be easily computed from any existing software that supports weighted two-way fixed effect estimators. Like anything like R, Python, Stata, you can easily use this. And finally, theoretically, I think this objective reweighting perspective is a powerful general strategy. So for example, if you replaced the least square objective for two-way estimator with an event study objective, you may be able to handle short-range dynamics. So, or on the other hand, you may also be able to handle continuous treatment. Like we have already obtained some results, some analog of the data equation in the case of continuous treatment, which look much more complicated, but you can get it. So with that, I would like to thank you all for your attention.
Great. Thanks a lot, Lihua, also for sticking to the time. Virtual clap, naturally, great presentation. There are interesting questions in the chat, but also due to interest of time, I propose we move now to the discussion and we will ask them afterwards. So I would give now the word, just a second, to Pedro.
Let me try sharing here.
Yes, please, you should be able, I hope. Great.
Can you all see my screen? Yeah.
Yes.
So first, let me say right away, I'm very grateful to be here, for the four speakers, like Clément, John, Brant, and Lihua for fantastic talks. and Andre for putting this together, like to unite us all. And I'm Pedro Sant'Anna. I'm a researcher, senior researcher at Microsoft. I'm also assistant professor at Vanderbilt. I was given this duty of summarize or discuss these 4 papers in 15 minutes, which everybody who knows me know that is mission impossible, right? I talk, and never ends. So what I'm going to try to do, it is unite all these papers together and give my view what they have in common, how they can be like, how these presentations, the commonalities, and like what they differ, and how we can move forward, like to improve science or to improve empirical practice, less ambitious goal. So just like summary, right? So Clément gave a very nice overview about state of the art, difference and difference literatures, right? So everything that happened in the last, a good chunk of things that happened in the last 4 to 5 years was succinctly summarized by Clément. And what he did is like, he split the talk in problems of two-way fixed effects and how we can solve them. I like that a lot. And he highlighted that like there is not one single procedure that should be always used. And I really like that point, right? So the different situations require different designs, different estimators. And that was for me the main takeaway message for his presentation. But everything that Clément talked was somehow holding parallel trends as an assumption that is constant, that we trust that. But then in practice, it's very common, like, so, well, you know, do I really believe in parallel trends? How I can pretest that? How I can check if that is a plausible assumption or not? Then John comes into play. I say, well, in practice, people do pretesting, right? He highlighted issues with pretest, but then he's like, also proposed some solutions to do sensitivity analysis on some type of violations. And I really like that as well. So, and then like Brent came, right? So the first 2 talks was mostly about, sorry, my daughter is playing around here on the floor and it's like making a mess. So that's the duty, like issues with like COVID and all that, right? COVID area. But I mean, just coming back, so Brent talked about continuous treatment and he somehow highlighted that with more variation in the data, like so richer designs, there are plethora of new parameters we can estimate, right? And some problems of two-way fixed effects remain, but also some new problems appear. And he discussed briefly how we can tackle those problems, how we can diagnose those problems, how we can detect it. So at the moment, the paper with the Brent presented is co-authored with me, right? We are more likely in the negative side. We don't have proposed any way on move the literature forward on how to improve practice, but it's an ongoing effort, and we're going to do that. Last, Li Hua just finished his talk. Like he said, well, what happens if people don't want to give up on two-way fixed effects? I'm very used to running two-way fixed effects regressions, right? I like that. So how can we kind of like, quote unquote, resurrect two-way fixed effects procedures, right? And the way he does that, like, well, instead of relying on parallel trend assumptions, he's going to say, well, let's consider assumption about the design of the experiment. Let's say that the researcher is comfortable on modeling the treatment allocation. And if you can do that properly, you can allow heterogeneity into a fixed effects, but like using this kind of clever reweighting schemes, you can bypass some of those challenges. So that's like overall view in the last 1 hour and a half, 1 hour 45, and how these papers connect. I have been thinking a lot, like when I saw all these things, right? I gave the summary, but the number one question I want you guys to remember, it is, what does unify all these papers? Why we put them together, right? So at the broad picture, the way I see all these papers like connected, it is that no matter what's the design, no matter what's like the question you're trying to raise, the main goal here across all presentations has been very clear. We all want to provide more reliable tools for empirical researchers. We want to connect econometric theory with econometrics practice to bridge this gap and move forward, right? So there are some like quote unquote different solutions, different problems, but the number one goal is moving science forward, moving empirical like research forward. And I think that's what I want everybody to remember, right? Different problems, different solutions, right? Main goal, we as a field, as a whole, as econometricians, like we are much better than we were 5 years ago, right? So that's the #1 message that I wanted to remember. Right, but now I'm going to try to go like papers by papers and summarizing the type of questions I usually get as well. So email, like I exchange on Twitter and so on and so forth. So first thing I'm going to go in and say, well, we know two-way fixed effects can be problematic. We have many different like new estimators. They're like heterogeneity robust. They embrace heterogeneity, right? But at the end of the day, how does one choose which one to use? I'm sure that Clément has gotten this message like 1 million times, right? Brent has gotten this question many times as well. John, Liwa, myself, right? So here is like, there is no answer for that question, right? Because this question is a very context specific and design dependent question that people have to have in mind when choosing. It is, well, is my treatment binary and is my adoption staggered? Right? Yes or no? If the answer is yes, I have a subset of procedures to do it. If the answer is no, I have another subset. So the choice of the design, the treatment type, it's really important. Second, what kind of parallel trends I'm willing to impose? Do I want to use all treatment periods as valid, like kind of baseline periods? Do I want to use just a subset of them? Do I want to condition for covariates? Do I want to like allow for like state-specific trends? So like unit-specific trends. So this is also going to guide which estimator, which design you pick. Right? So are you comfortable if you allow for treatment turn on and turn off? Are you comfortable ruling out carryover effects? Right? So like dynamic effects, yes or no? What is the question you're trying to answer? So overall, I mean, there is no estimator that dominates all the others. And for my view, like Clément's presentation, this was very clear, and I kudos to him. Right, and to Xavier, this message should be stressed more often in the literature, right? Because we all here, I mean, there is no way one paper going to solve gazillion problems. So this is what I really like it. Right, now moving to John's paper, right? So what he did is like, well, parallel trends is kind of quote unquote magical, right? We don't know where it's coming from. I mean, how do we trust that? How we don't trust that? How do I know if this is plausible or not? So practice what we do, right? We kind of like rely on pre-testing, but pre-testing has some issues, right? John highlighted some of these issues in one of his paper, but then in this companion paper, he doesn't sit in his ivory tower and point figures to everyone. What he does together with Ashesh is like he proposed several new tools that you can take serious these challenges and try to improve it. I really like that. And in my view, combining these sensitivity analysis tools that like John and Ashesh put forward together with this heterogeneity, robust difference and difference procedures, I mean, should be adopted further to kind of like make difference and difference analysis like transparent and more reliable to know how this is actually like, how much should we actually trust, I mean, a kind of degree of trust on our estimation procedure in our empirical results, right? I want to show like this was not really like highlighted by John, right? But I want to show this is actually very possible, right? So we have been working together. So John, Ashesh, Brent, myself, on making our companion R packages compatible with each other, right? And here I just have a like kind of example on how we did this, which is to combine the DID R package together with the honest DID R package to show how you can do this. And we're going to do this in the context of the application of effect of minimum wage on teen employment that Brent and I consider in our paper 2021, Callaway and Sant'Anna. Right, so I have some codes here. I can make these things available. It's just like a couple of lines of our code describing what we do it, how we package, which package we have to install. This is just telling, well, I'm going to do conditional parallel trends, right? I'm going to estimate an event study to see the effect of raising the minimum wage on employment. And what I get, it is this kind of plot, right? So this plot here, it is like whatever I have in the negative time here, it is pre-treatment period. In the like positive event time, it is post-treatment period. We see some positive effects, right, on the post-treatment period. But if we look at pre-treatment period, say, well, I mean, parallel trend here is very like plausible to be violated, right? The period, the -2, for example, these uniform confidence bands do not go over 0. And visually speaking, as John have stressed in his presentation, you can fit a straight line from like -5 until 0.3. It's going to cross all the points, right? So do we rely, how much we trust this conclusion that like there is a negative effect of minimum wage on like employment, teen employment? So what do we do? So well, when we wrote this paper, this is like where we stop, right? So there's nothing much we could do it. Now, thankfully, we can combine different tools available in the literature. We can combine Callaway and Sant'Anna. I'm pretty sure we can also combine like the Chaisemartin and the auto-Fourier procedure because they are very like connected to us, at least in the staggered case, right? We can put these things together. And once we get this event study in place, we can ship things to this like sensitivity analysis tool that John has highlighted in his presentation. And we're going to get something out of like this, right? So the blue confidence interval here, it is what we report. This is the instantaneous treatment effect. So this event time equals to 0, right? And we see it's a negative effect as we have seen in this previous slide here. But now it's like, well, what happens if I allow my parallel trends to be violated as a proportion of the maximum violations I see in pre-treatment periods, right? So this M bar, it is this constant that like how much violations I can allow, right? And you can see like, well, it crosses the 0 line here. So 0 is included in this confidence interval when this M bar is around 0.9, right? So this tells like, well, for our conclusion, we can allow for violations of parallel trends up to 0.9 times the maximum violations we see in pre-treatment periods, and our results will not, it will still remain. We're still going to find negative results. If we allow for bigger violations, right, our results are going to include 0, and we're going to have less certainty to say that this, that we're not going to be able to rule out there is no disemployment effect. Right, so in practice, what I think is missing, right, it is how do I pick these parameters, these M values for the sensitivity analysis, right? So here it has a very good intuition. What is the meaning of M bar? But in general, is 0.9 okay? It is 1 okay? Is 1.5 okay? So this is what I think we can do like together as a collective effort to kind of like try to move this forward. Right, another central theme on difference and difference methods, right, is about heterogeneity and parameter of interest. So as Clément was mentioning in his discussion, right, it's the literature has put a lot of emphasis on how we can interpret beta on variations of this 2A fixed effects regression, right? So I have run like an outcome of interest against unit fixed effects, time fixed effects. I have this DIT dummy variable here. It takes value 1 if I am treated in period T, 0 otherwise. Right, and then once we allow heterogeneity, allow units to respond to treatment differently across time and across different units as well, somehow we can characterize this beta as a weighted average of cohort and time-specific treatment effects. Right, I'm simplifying things here, I'm changing notation, imposing additional assumptions, but the main message here it is these weights, this WTG, right, are not guaranteed to be convex. Right? This is just a fancy way of saying that, well, these weights can be negative, right? And these weights can be negative, that's like the elephant in the room. So this is like how the literature have evolved. The question is, what if these weights were actually convex, right? So there were some questions in the chat. So well, what happens if I have just a small number of negative weights? Then what? Is this fine, right? And this is where I think like the message has not like synced so much among applied researchers. It is that we have to have the discussion about what we're trying to estimate. What is a target parameter, right? The instrumental variable literature have been discussing this for 20 years or so, right? You have like they're like, if you do IV, you're going to estimate an average effect among compliers. The MTE literature has been like complaining about that. You don't care about compliers and blah, 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 blah. What is going on here in this weighted average representation is very similar in spirit, what happens there. And I think it's interesting to like shape the questions, see if you care about these weights or not, and like to help better mapping econometrics techniques or estimation procedures to answer causal questions that we actually care, right? And when treatment is continuous, this is becoming even more like important, right? So like Brent presented the continuous paper that is together with me. I mean, let's consider the simplest case with a continuous treatment, right? Nobody's treated in period 1. Some units are treated in period 2 with different dosage, and we still have units who remains untreated in period 2, right? So I have like a set of units never treated. Some units are treated in period 2 with different dosage. And I run this two-way fixed effects regression, right? So I get this estimation, which is something that like Clément have considered in his paper, like the RayStud paper, like the fuzzy DID, which has some flavor of this as well. But he's like, we don't have fuzziness, right? But it's similar problems. So in this situation, like I can give very different interpretations for beta depending on the building blocks of my analysis, right? What do I mean by that, right? So under strong parallel trends, right, which is a stronger version of parallel trends, we can decompose that beta coefficient in terms of different building blocks, right? So if I care about slope effects, right, about like the average effect of incremental dosage, right, and I want to combine this dosage, I mean, we show in the paper that we can, this beta to fixed effects can be written as a weighted average of this average causal response, right? And all the weights are non-negative and integrate to 1. However, if I do not care about average causal effects, but I care about somehow the average treatment effect, so the level effect, I have an alternative decomposition where now my weights are non-convex. They integrate to 1, but they are non-convex. What is striking to me, it is like we have same assumptions, same estimator, very different interpretation, right? Which one I'm actually trying to estimate? I'm not even talking about the nature of the underlying weights, which is driven by the estimation method, right? But the same estimation can have very different interpretations depending on the building block, right? Depending on the kind of question that I'm trying to answer. So in my view, right, whenever it's possible, we should be clear from the very beginning what we're trying to estimate, right? Because that's going to help us like to communicate better identification assumptions, estimation methods, and so on and so forth, right? But this is all telling, like, starting from the position where I'm assuming researchers are willing to give up two-way fixed effects regressions. But what happens if they don't want to give up? I like two-way fixed effects regressions. I'm very comfortable with that, so I want to stick with this. And this comes Lihua's paper, right, who shows that when a researcher is implicitly committed to use two-way fixed effects regression.
Pedro, I apologize for maybe please 2 or 3 minutes more. Then there will be also
I just need
replies.
1 more minute.
Great.
1 more minute,
Thanks.
I'm done.
Thanks.
So once I have run this two-way fixed effects regression, right, how can I resurrect? Right? They want to allow for general binary selection, right? General treatment selection, but they don't want to rely on parallel trends. So how they can do that? Right? They can do that taking a stand on how units select, on modeling directly this selection mechanism, right? And then in the paper, they say as long as this model is good enough, we're going to be able to kind of like resurrect the two-way fixed effects for a particular easy to interpret causal parameter, the date. Right? So I think what is very shiny about Lihua's paper, it is that he's not relying on parallel trends. So why this is important? Because he can estimate many other parameters because of this latent unconfounders. So he's not tied together to estimating an ATT, right? He can use different groups and different designs, right? And I believe it would be awesome to stress this point more, because with different assumptions, I can estimate different parameters I can answer more questions, right? And I can say, well, in difference and difference, sometimes I cannot answer these questions, but now I can answer these questions using these procedures, right? And I would love to see more discussion about this nature, like overall. So to wrap it up, right, we are living in very exciting times. There is a lot of work still to be done, right, to move this literature forward, to connect the pieces. And I mean, I really like the idea of econometricians, like all of us, working together with empirical research side by side to help each other to improve better practice, right? So thanks, that's all I have.
Thank you, Pedro. Great discussion, and I hope this will stimulate responses. I would just point to also to the listeners that there will be an open discussion. We're a little bit lengthy due to 4 speakers and so on. So I hope you will wait also for the discussion. But I give now the floor, I just suggest in the order of the presentations, to Clément, who has to leave a little bit earlier. Please, if you have any response to the great discussion.
Okay, thanks, Andre. Thanks very much, Pedro, for the very interesting discussion. Yeah, I think we completely agree that there's not going to be a one-size-fits-all estimator, and that, you know, depending on the design and the situation, you're going to be preferring to use, you know, one or the other of those newer estimators. And yeah, like I think kind of providing a taxonomy of cases was actually one of the goals of the survey, to help applied researchers navigate this kind of jungle of estimators that's out there now these days. I also agree that even though, you know, like my presentation and John's presentation could seem very unrelated, in the end of the day, they actually are not. And I think you were it's really important to realize that even though John presented his paper in the context of a simple diff-in-diff with no variation in treatment timing, actually these methods can also be used in the more general designs where the issue of heterogeneous effects arises. So I think it was a really interesting point that you were making here. And I think that actually also, related to your first point, when we start about thinking of a world where, you know, parallel trends may not exactly hold, it may rather be like a first order approximation to reality, which maybe is not too bad, but is not perfect. And we start thinking more in terms of John's world, then I think there are actually interesting consequences for the type of diff-in-diff estimator you want to use, and how you want to test parallel trends, etc. So I see also that, like, you know, the merger of these two literature as another promising area for future research. And yeah, and I also think that your decomposition with Brantly, where in the continuous treatment case, where you show that depending on whether the building blocks are going to be like these discrete derivatives or these continuous derivatives of the potential outcome function, it's kind of a neat and subtle result, which shows that, you know, you need to be very careful as to what are your effects of interest. So I think it was you did a good job, because you had like 4 papers to discuss in a limited amount of time, and you actually brought some new substantive elements to the conversation. So I really like that.
Thanks. Maybe Jonathan?
Yeah, so thanks, Pedro, for the great discussion, and Pedro and Brant for taking the lead on integrating our R packages. I think that'll be really great. Yeah, so I guess the one thing I would respond to is, Pedro, you talked about kind of how do you evaluate the, you know, the sensitivity analysis parameters, and, you know, that's sort of having a economic interpretation of the sensitivity analysis parameters is like a really important thing in sensitivity analysis. You know, if I tell you your thing is robust up to 2 apples and an orange, you know, that might be like a mathematically robust statement in some framework, but it's not very useful. And so, you know, when we first wrote this paper, we originally had robustness to deviations from, you know, linear trends, which we were sort of coming from the framework where people often estimate parametric linear trends. And so that was a natural thing to deviate from. But then people had a hard time thinking about sort of what is an M deviation from a linear trend, you know, what values of M are large. And so that's why in later versions, we introduced these relative magnitudes things, which I think are a bit easier to interpret. You know, you can say I'm robust up to the max in the pretreatment, or, you know, 2 times the max or something. But I think there's still questions of, what do we want robustness to? In the example I gave in my talk, we were robust up to m equals 2, so we were robust to twice the max. On the other hand, this is a reform that happened in 2008, as we all know. The economy, subsequent to 2008, in a lot of ways was very different from things previously, and so. Clément probably knows more about the French restaurant industry in 2009 than I do. But, if this was, I was studying this, I would kind of want to know economically, what were the shocks to restaurants like? How different were they to other industries? And how does that compare in 2009 relative to other, pre-treatment periods? And so, I think as econometricians, we like to focus on sort of just statistical parameters and tests and stuff. But my hope is that with some of this sensitivity analysis stuff, it's a tool that people can use to kind of bring the economics back into the econometrics that they're doing. That, rather than saying I'm robust to m bar equals 2 and everyone in the literature knows, something greater than 1 is okay. I'd rather this be a thing where we say, we're robust to twice the max. And, we know something about the context. So we ideally know sort of, is it plausible that the confounds in 2009 were twice as big as, the confounds in 2007? And, if we know something about what happened in France, in the restaurant industry in 2009, then that, we can bring that information to bear to sort of evaluate whether the sensitivity analysis parameters are sensible or not. So my hope is that this is a statistical tool that can be sort of integrated with economic knowledge.
May I chime in to ask a question
Please.
to John about that, actually? So I'm wondering if you've ever thought of considering that, like some kind of meta model where those deviations from parallel trends are actually drawn from a distribution and they are IID, and then if if the number of time periods goes to infinity, that would imply that in the post period, the deviation from parallel trends cannot be larger than the max prime before that, something like that. That would be a way of rationalizing m is equal to 1, essentially.
Yeah, that's a good point. I mean, so I think, we have minimax bounds basically, like based on the worst case. I think, you could have some type of Bayesian model or, empirical Bayes type of things where you thought about the violations as coming from some distribution and you could deal with the distribution. We haven't done anything with that, but I definitely agree that would be like an interesting direction to go. I think, unfortunately, often these settings have very few pre-treatment periods. So like in my review of papers in the AEJ and AER for my pre-testing paper, the median number of pre-treatment periods, I think, was 4. So, t equals infinity, maybe a little bit far away as an approximation in some of these cases, but definitely agree, having more pre-treatment data is good. And when you do have that, potentially doing some of these, like, estimating the distribution of shocks and then some type of stationarity assumption, I think could be good. I like that suggestion a lot.
Thanks. Maybe we continue with Brantly now.
Okay, thanks. Yeah, Pedro, I don't really have any responses about my paper to your comments because I've heard them before. But I do think, I do have a couple of general comments. I think so. A lot of people have been talking about John's paper. I sort of agree with the idea that Pedro said that, like, there are often, I think, different solutions to different setups in this literature. But I do think a good sort of like general idea for like what should you do is like do some kind of like modern sort of difference in differences that's relevant to the case that you have, and then do John's stuff after. I think that there are lots and lots of like our stuff when we did this stuff about the minimum wage, we didn't know John's stuff at the beginning. And I think our paper fits into the framework that lots of applications fit in, that it looks like parallel trends holds ish, and then you see some effects afterwards. But I think you kind of like, you show these sensitivity analysis plots, and I think they're very persuasive. Like, you like what our results are in the application are that it looks like there's some negative effects of the minimum wage on employment, but they're not super robust. I mean, you have to believe something. This is not overwhelming evidence that the minimum wage is reducing employment. And I think that's a very sort of effective pathway for many, many applications. Is that like you start off in an application, you don't know if parallel trends holds or not, but this sort of gives you a way to like circumvent both the issues with two-way fixed effects regressions and to I think very carefully and clearly about how robust your conclusions are to plausible violations of parallel trends. I think also one other thing on that, I think, you know, once you move to like a staggered treatment setup or setup where people can move into or out of treatment, there's more information that's kind of potentially sitting there about ways to think about what kind of violations of parallel trends are showing up. I think one other thing I think for us as a group, I think you noticed from the comments, there's a lot of interest in code. And I think that sometimes for us that like the returns to writing code can be quite low, but I think in terms of like actual, you know, I mean, returns in terms of getting tenure or something like that. But I think the returns in terms of being useful to the profession, I think can be quite high. So, I mean, I think this sort of suggests that there's a lot of usefulness for like writing unified methods, writing methods that work together off the shelf for users. And then the last thing I have is about Pedro talking about weights. I like the point about like noticing that this is similar to like discussions about local average treatment effects in MTE. But I do think that one thing that's different there is, if I understand the debate about weights and MTEs correctly, my sense is that most people who have been advocates, say, of weights, is not that like the parameters of interest that people say in the MTE literature are not more interesting. It's just that you can't identify them without making stronger assumptions. But I don't think that the difference in differences literature is like that. Like we can identify more interesting parameters and recover those from the data that we have. So I think that there's, I think that the parallel is interesting, but I think the problem is maybe not as deep as in that literature, and that you can kind of easily do better than sort of just like taking any kind of positive weighted average of underlying treatment effects. That's all.
Thanks. Thank you a lot. Probably Juan.
Yeah,
Close
so
this.
thanks, Pedro, for the
Thanks.
insightful discussion. So maybe to respond to your point on how I foresee people using this first. So I think as with the cross-sectional data, so this is a great question. So as with cross-sectional data, you see that we have two components to model in principle. One is the treatment assignment mechanism. The other is the outcome model. So mathematically, these two things are symmetric. Like it's hard to tell which one is easier to model or not. But in practice, there are many cases where these things are very asymmetric. So the state of emergency example I mentioned is a case where you have a lot of information about the assignment mechanism, but you have very little information about the outcome model. So I think overall, the general message is that we need to leverage our information. So in some cases, if there's very little variation in the assignment model, then we should go for the outcome model-based method. So our method hopefully can bring up another way to think about the problems. So that's like one thing. And the other thing is, so I think a fundamental difference between our methods and the other methods are like, in the literature, most of the methods are based on aggregation. So you first define your target parameter, and then you find each component, and try to find an estimator for each component, and then using the same weighting schedule to get an overall estimator. So even an imputation-based method is like that. But our method is based on reweighting objective. And so eventually, they are the same, but I think the idea is a little bit different. So for example, now someone asked in the Q&A, which is an excellent question, that how are you going to combine this with event study model? So what I talk about doesn't assume dynamics, but in principle, you can also assume dynamics in the form of event study model. So you can still imagine that you take the objective and then you reweight it. You get an RIPW estimator. And of course, there are much more work to do to derive the condition for that capital pi. But in principle, you can work on that. And also this can work for continuous treatment work, even continuous time. So I think in many cases, like reweighting objective is another strategy to derive things. And one final comment about this weighting. So I think we all talk about negative weights, but there's something I didn't have time to go through, which is, so I don't know, have you noticed some conflict, like seemingly conflict that in the previous literature, people say the two-way estimator has negative weights. But in our work, we show that for randomized experiment, two-way estimator will converge to date. And date is definitely a weighted average of everything with positive weight. So these two arguments seems to conflict with each other. So what's the point here? So the point is, actually, when people talk about negative weight previously, they are talking about the weights conditioning on the assignment. So in other words, you got a bunch of weights for different unit I, different time t, and you know that unless you have more assumptions, there are some I and some t for which these weights conditioning on the assignment are negative. But if in your application, you believe there's a fair amount of variation in your treatment assignment, then the weight you're ultimately interested in is the unconditional weight, just like what happens in the cross-sectional case. So it turns out what we show is after this actual conditioning, the negative weight issue can completely go away. So that's one point that may be worth noting. And I think there's something really deep there and worth further discussion. And that's my comment. Thank you.
Thanks. Thanks a lot. Okay, Pedro, anything further from your side?
I mean, from my side, it's like as I say, I already talked so much. So if I start talking more now, it's like it's over. Well, just for Liu, I think, I mean, the last comment, it is more about the underlying assumptions behind the scenes, right? So in difference and differences, you have parallel trends, right? So I mean, it's compatible with conditioning on weights, right? So it's compatible with conditioning on assignment. So that, I mean, I think Clément is the best person to kind of like chime in and discuss that, because I mean, I'm not the negative weight person. So, but I mean, apart from that, I don't have anything to add. Just like thank everybody for like great talks and engagements, and I really appreciate it.
Maybe Clément, if you have anything, but otherwise.
So shall I add something here?
Okay.
Yeah, so I think that's right. Yeah, so based on your assumption, but more generally, I think beyond assumptions, it's about what source of randomness do you want to take into account, right? So even for cross-sectional data, ignoring all the parallel trend type of thing, then you could either conditioning on the potential outcomes as in design-based inference, or you could conditioning on the assignment as in outcome-based inference. But also you can take both the randomness into account. So here, I think the same thing carry over to the ID setting or to the panel setting, where if you further consider the randomness of the treatment assignment, then the negative weighting issue could be less severe than what we talked about before. But it really depends. Yeah.
Thanks. Maybe now we go to the open discussion. I thank also to the attendees who waited until now. I will try to pose a thank to all the speakers and Pedro who responded many questions, I think, in the meantime. But there was one, for a start, a very general one, which relates, I think, to all presentations, to the weighting that Lihua just mentioned, and so on. What is the comparison of the approaches presented to the synthetic control method? There was one reply in the meantime that some of the issues, I think, from Jon's presentation could be solved by synthetic diff in diff from Arkangelsky and co-authors. So what is the relationship with SC, I will say? Maybe to all, because we know it is related.
Yeah, I'll start. I think that's a hard question, right? Because the identifying assumptions are very different. I mean, whatever that means, right? So I think like the starting point of difference and differences, it is the parallel trend. The starting point of synthetic controls is somehow learning about pretreatment trends using lagged outcomes, right? So when one is going to be more appealing than another, it has to do about, I mean, this distinction. For me, it's very hard to make both of them like compatible, just because for the sake of identification arguments, I always struggle to compare to connect the two, right? So I think that's where I would stop. Otherwise, I say stuff that I'm not really clear, right? So that's where I think it's just like the starting point is very different and it's hard for me to contrast.
Thanks. Also others, maybe? Possibly in relationship to the synthetic diff and to many approaches that are developing synthetic interventions, distribution of synthetic control, distributions were mentioned related to pretrends.
Maybe I can chime in a bit. Yeah,
Please.
so I think synthetic control is looks like a very similar problem as DID. So as Pedro said, it's based on different set of identifying assumptions, but maybe there's a way to unify them. So for example, from the recent synthetic diff and diff literature, we can see that underlying structure is like a factor model. So that's like a compromise of the parallel trend assumption, but it's not completely wild like anything. So there, for example, you can imagine your outcome model is a factor model. On top of those two-way fixed effect, you have something else. Then potentially you can combine with something else and to deal with that. For example, in our context, you can revise the objective by adding the factor modeling part into the objective and reweighting it. But I think the main challenge, one of the main challenges is that usually synthetic control is deal with the cases where there are only a few treated units. So here, making inference is very challenging. So you see that if you read those papers, then in terms of consistency, they can allow for one unit or a small number of units. But when they go for inference, they still need the number of treated units to go to infinity and number of pre-treatment periods to go to infinity, unless you assume some very simplified parametric model. So I think on the one hand, they are similar mathematically, but on the other hand, due to the small number of treated units, things become much harder. So for example, in this case, it's hopeless to identify ATE. So the only thing you can hope to identify is ATT.
Yeah, just to follow up with that, I mean, I think like I really like the factor model with finite t as well. I really like Brent's like paper with his student who is like, well, what happens if you have like a factor model? I mean, you have a missing factor model, right? So you observe some of the fact. I mean, you can proxy. Say you observe age, right? Which you have covariate specific trends on age, but there is something else out there that you cannot measure, and that if you control for that would capture. I mean, I think it's possible to identify the effect in like with short t, but that's Brent's work, not mine. So I'm just poking Brent so he can speak.
If I can find the unmute button there. No, I agree. I mean, I think that they're like, it's interesting to point out factor models because I mean, they do seem to like be related to the map between difference and differences and synthetic controls. And both of those, I mean, I think, so the paper that Pedro mentioned, other people have talked about kind of like thinking about basically factor models as a way to generalize difference and differences, but they also serve as kind of the motivation for synthetic control. So, I mean, I don't know if I have a full explanation there, but I think that is the right place to be thinking about kind of the connection between the two. But I mean, I think these are well taken points about like, you know, most factor model papers, if they're geared towards treatment effects or not, are large T sort of papers. Now, that being said, my paper, some other papers, there are ways to identify treatment effect parameters in short T settings, but you need extra information somehow. And those can look like independence assumptions of like error terms over time. They can be, our stuff is about like that paths of outcomes don't depend on particular covariates. So there can be ways to relax parallel trends in, I think, nice ways like factor models. But I think often, I mean, one of the things about difference and differences is if you have two time periods, you can do this. If you want to start thinking about much more complicated sorts of trends, then you're going to start asking more out of your data or asking more out of the assumptions that you're making. And so, I mean, you can do this. If you have better data, you can make weaker assumptions, but either there's going to be probably going to be extra requirements on the assumption side or extra requirements on the data side that just aren't there with differences.
Yeah, I don't have much to add. I mean, I agree. I think there's more work to be done to sort of integrate differences and parallel trends, differences and synthetic controls into a unifying framework. They kind of live in different theoretical spaces right now, I think, which makes it a bit hard. I think the one thing I would add is, I think with any of these methods, people often want to show some placebo or pre-treatment, thing that doesndo show effects. So, I estimate my synthetic control matching up only up to treatment date -5, and then I, see do they move in parallel between -5 and 0. And I think I feel fairly confident saying that, if you do that, which is essentially a pre-trends test, that there are probably similar issues of we're not sure what the power of that is, and we're not sure, if you condition on passing that test, it probably is going to affect inference in some way. So I think these types of, if we're going to condition on a placebo test, that's going to have similar, types of issues in other contexts as well.
Thanks. I would point also to two further questions. One was in the Q&A, I think also very relevant, probably an interesting relationship to the recent work of Jeffrey Woodridge. The attendee is asking, he seemed to frame it as a mechanism for using perhaps more familiar tools approaches, but still recovering valid estimates. Maybe Pedro was first one, but naturally all others.
I can go there. Yeah, so I mean, what Jeff is doing, it's similar in spirit with like the work of Sun and Abraham, like Callaway and Sant'Anna, the Chaisemartin, the Autofourier, right? So I mean, Gardner as well, Borussiak and Joravel. So like this universe of new papers, what he's proposing there is similar. The main difference that I see is that he's explicitly allowing other types of heterogeneity when doing the two-way fixed effects, right? So somehow it is like Sun and Abraham with covariates, right? So if you combine the two procedures, so the way I see this new paper by Jeff, it is like, well, how I can incorporate covariates in the procedure that Sun and Abraham has proposed, this approximation, right? And yes, he's essentially like interacting covariates with like cohort dummies and like time fixed effects to explicitly allow more heterogeneity. So they are all connected, right? So they are all in the same family of embracing heterogeneity. But in the way he's doing it, the way I see it, it is like explicitly modeling that heterogeneity. So the
Pedro, can I just add? Oh,
go ahead,
sorry, keep going. I thought you were done.
Yeah, the thing is, I'll say that that's pretty much it.
I was also going to say, I think those ideas are very much similar to what's out there in the literature. In fact, when I've done this on my computer, I get the exact same estimates as if you do this Borussiak, Joravel, and Spies imputation stuff. But so my sense is that it's very similar to other procedures in that, like, if you go to like the textbook case of two-period difference in differences, my sense of the killer feature of doing a regression there is that you run a regression and you can read off the standard errors from the regression, and you're done. I think with the new stuff, like you can so still with Woodridge's stuff, you're doing kind of a two-step sort of estimation procedure, and so I think that kind of loses the killer feature sort of aspect of the two-way fixed effects regression to begin with, that you can't just run one regression and read the results. You need some software package to run a regression, do something else on top of it, and report the inference procedure. And I think that's kind of the same flavor as like all the sorts of procedures that are out there in the literature. Kind of make a good comparison, aggregate it into some treatment effect parameter of interest, and then get the software to report the results for you.
Thanks. Probably a second question related to this. There was a very recent paper from Susan Atey in YASA, in Journal of American Statistical Association, and other literature implementing matrix completion estimators. Could those estimators also play a relevant role for the development of difference in difference literature related to missing problems of missing counterfactuals and so on?
I'm happy to take that. I mean, I think, you know, in causal inference, basically you have to impute some missing potential outcome, right? So, you know, we have treated units, we see Y1, we don't see Y0. And so parallel trends gives you one way of imputing the missing outcome, and then matrix completion is a different related way of imputing the potential outcome. One thing I like about the matrix completion stuff is they basically impute like a y hat 0 for every treated unit. And so then you have a panel data where you have the actual outcome that's like Y1 for the treated units, and then you have a y hat 0. And then once you have that data set with the sort of estimated truth table, as they call it, then you can aggregate it any way you want, right? So like once you have that, you know, essentially panel observations with imputed counterfactuals for everyone, you can take the difference and then you can aggregate it in whatever way that you like. And so I think kind of the approach there of dealing with heterogeneity is very flexible and is sort of compatible with a lot of the stuff that, like, you know, Pedro and Brant have done, where you can say, you know, I want this weighted average. But I think that just the main difference is that the way of imputing the Y0 is a bit different. And it'd be interesting to learn more about, you know, when one works well versus the other.
Maybe I can add a little bit on that. So as John said, basically the matrix completion is an imputation-based method trying to impute Y0. And so previously people are using explicit model to do the imputation. But here, this matrix completion is using the low rank structure to do the imputation. So it's based on some regularization. And the point I want to add on that is this is a case where the assignment model will be very useful. Because if you're familiar with the development of matrix completion in the CS literature a few decades ago, so there they consider the problem where the entries are missing at random. So you have a matrix and you have entries that missing the missing mechanism is independent of the row and the column and the size of the measurement. So there, the result is very surprising that if you have n by n matrix, you only need number of units, number of observed entries linear in n. But here we are in a much more challenging setting where things are never missing at random. So usually for staggered adoption, there's a whole chunk of missing. So this problem is more challenging. And also whether matrix completion can be successful depends on how the missing mechanism interact with the outcomes. So here, I think there's a whole lot more to do on top of the CS literature to think about, in our case, suppose we have, say, a Cox model, then how does that render the results of the imputation? I think that's a very interesting open question to answer.
True. Thanks. Anybody else? Thanks a lot. Great. If there are no further questions also from attendees, I apologize. We give the word to the questions that are provided. I would end with one final question that was dismissed, but I think also important. Naturally, all of those materials, the presentations, I hope, and so on, will be online, providing all of the respondents which were around the world to get access to the materials that were presented. So I thank greatly to all, to the excellent 4 presentations. Unfortunately, Clément had to leave a little bit earlier, to Pedro for his excellent discussion and great help in organizing the webinar, to all the questions, all the attendees. I hope we answered at least most of them during the webinar. So thank you all. A note to all, we continue, YoungStatS continues in start of February with the webinar on symmetric inclusion processes and sticky Brownian motions. So from probability issues, hopingly we will very soon discuss topics that were also discussed today. So thanks again to all. The webinar was recorded, it will be put online. I saw there were quite several spectators also on YouTube. Thank you, and hoping to see you soon.
Thanks very much, Andre.
Thank you so much, Andre.
Thanks. Thank you.
And I just want to
everybody.
say that if there are any attendees who have outstanding questions, feel free to reach out to me by email. And I imagine Pedro and Brant and Lihua would also be happy to answer any questions offline. So thanks very much.
Thank you. Thanks to all again.
Thank
Bye.
you, everybody. Bye.
Bye.
Hey, Brant.
Hey, Pedro.
Was Sophia very loud?
Not too bad. If you know, the first time I wasn't
Oh,
paying
wait,
attention to like the
let's